Welcome to the Explainer. Today, we are tearing into something I like to call the aerostop paradox. We're going to deconstruct the invisible, just totally meticulous engineering that actually stops the world's most massive, high-performance machines. It's a fascinating dive into why these incredible aircraft have to start stopping long before the rubber ever even meets the runway.
All right, to really wrap our heads around the sheer scale of the engineering problem here, I want you to picture yourself sitting by the window of a massive airliner. You're strapped into a machine weighing hundreds of tons, and it is absolutely screaming toward a runway at 270 kilometers per hour. Now, if you remember your basic high school physics, kinetic energy equals 1/2 mass times velocity squared. Bottom line, the amount of energy a heavy, fast-moving airliner carries is just astronomical. And right beneath you is a stretch of concrete that, quite frankly, looks way too short to absorb all that mass and kinetic energy. So how on earth does it happen without ending in total disaster?
Well, it's super tempting to think of stopping a plane like stopping a car, right? Like you just touch down, slam on the brakes, and you're good. But listen, if an airliner relied on wheel brakes alone, a safe landing wouldn't just be difficult, it would be physically impossible. The brakes would completely melt, the tires would explode, and you'd run out of runway fast. So instead of one simple action, aircraft braking is this highly complex, multi-layered, sequential process. It's like a perfectly choreographed dance where aerodynamics, mechanics, and electronics all have to work together in split-second harmony to pull this off safely every single time.
Okay, let's dive into this. We are going to break down this carefully calculated scenario into 4 distinct phases. 1, aerodynamic braking in the air. 2, surviving touchdown. 3, destroying lift. And 4, reversers and megajoule brakes. Starting right off with phase 1, aerodynamic braking in the air. You see, the very first step of this perfectly engineered sequence doesn't actually start on the concrete. It begins hundreds of feet up, long before the plane even makes contact with the ground. Because actually, a pilot's first tool isn't a brake pedal at all. It's the wings themselves. The pilot deploys flaps, those movable panels that extend down from the back edge of the wing. From an engineering standpoint, doing this changes the wing's camber, its curve, and significantly increases its overall surface area. And this is just a brilliant aerodynamic trade-off. By extending those flaps, the plane generates significantly more lift, so it can fly much slower without stalling and dropping out of the sky. But at the exact same time, changing that airflow creates a massive amount of aerodynamic drag. The aircraft is literally using the thick, lower atmosphere air as a brake to shed speed while it's still flying, making sure it reaches the edge of the runway at the absolute lowest safe speed possible.
Next up, phase 2, surviving touchdown. This is all about the immense strain on the tires, and man, this is the brutal moment of truth. This moment is incredibly violent. The engineering tolerances required to survive it are totally awe-inspiring. Think about this. Within a fraction of a second, the stationary, incredibly heavy rubber tires on that landing gear have to accelerate from a dead standstill to over 250 kilometers per hour. And because of their resting inertia, they don't just instantly start rolling. No, the friction generated in that split second is so intense that the rubber violently slides against the runway concrete before it finally catches and spins up. That right there, that is exactly why you always see those massive, iconic puffs of blue smoke right at touchdown. Now, because of that extreme friction, relying on regular atmospheric air inside these tires would be an unmitigated disaster. Instead, they are filled with dry nitrogen. And dry nitrogen is absolutely essential for survival here. The key word being dry. It doesn't contain any moisture, which means it won't freeze when the plane is soaking at -50 degrees up at cruising altitude. But more importantly, while moisture expands unpredictably when heated, dry nitrogen maintains a highly predictable pressure even under severe stress. Plus, it's an inert gas, meaning it doesn't support combustion. And trust me, that is critical given the insane heat generated the second those wheels hit the tarmac.
And speaking of heat, the thermal shock here is genuinely amazing. Upon impact, the surface temperature of those tires suddenly spikes to 200 degrees Celsius. Without the predictable, non-combustible nature of that dry nitrogen inside the tire, a catastrophic blowout under that kind of instant thermal shock would be pretty much guaranteed.
Which brings us to phase 3, destroying lift using spoilers. This is the core paradox of the entire landing sequence. So, the wheels are firmly on the ground, but the plane still isn't ready to use its heavy mechanical brakes. Why? Well, because the wings are still trying to fly. As long as there's residual lift coming off those massive wings, the aircraft's full weight isn't actually resting firmly on the landing gear. And if the weight isn't pressing down on the wheels, the mechanical brakes can't get any traction or bite on the pavement. So the immediate job is to, quote, destroy lift. Right after touchdown, you'll see these panels on the top of the wings violently tilt upward. Those are the spoilers. By disrupting the smooth airflow over the wing and just killing that upward force, the spoilers effectively slam the aircraft's full mass of weight straight down onto the landing gear struts. Only now can the mechanical brakes actually do their job without just dangerously skidding the plane all the way down the runway.
Finally, we enter Phase 4, reversers and megajoule brakes. This is the final handoff in our deceleration sequence, where the engines and the heavy-duty mechanical brakes dump the remaining massive amounts of kinetic energy. Now, what's really interesting is how the deceleration workload is distributed. While the spoilers are slamming the plane down to destroy the lift, the pilots simultaneously engage the thrust reversers. Instead of pushing the plane forward, the engine's tremendous power is actively redirected by these mechanical cowlings to push against the forward momentum. On a standard dry runway, thrust reversers handle about a third, or 33%, of the deceleration. But on a snow-covered or wet runway, where hydroplaning is a real, terrifying risk, they become absolute lifesavers. They provide massive stopping power that is completely independent of tire friction.
Which brings us to the absolute harshest part of the stop, the mechanical brakes themselves. We are not talking about simple steel brake pads like you have in your car. Oh no, these are heavy-duty, multi-disc assemblies engineered from advanced carbon composites. Why carbon? Well, steel would just warp or completely melt under this kind of strain. Carbon composites are lighter, sure, but they actually become more efficient at gripping as they get hotter. Their entire job is to absorb hundreds of megajoules of kinetic energy in a matter of seconds, basically transforming the forward motion of a 500-ton aircraft into pure, concentrated heat.
And the amount of heat we're talking about is staggering. In just those few seconds of heavy braking, these carbon composite assemblies can glow at temperatures exceeding 1,000 degrees Celsius. Honestly, this actually solves a pretty common travel mystery. If you've ever wondered why your plane sometimes just sits there on the taxiway for a few minutes after landing, seemingly doing nothing, yeah, it's often because those brakes are glowing red hot. The pilots literally have to wait for them to cool down before it's safe to slowly taxi and park at the gate, otherwise they run the risk of melting the tires right from the inside out.
You know, it is incredibly easy to look out the window at a 500-ton machine stopping on a dime and think it's just modern magic. But as this explainer highlights, it isn't magic at all. It's a perfectly engineered sequential system built on exact calculations and a deep, deep respect for the laws of nature. From the aerodynamic drag of the flaps, to the dry nitrogen in the tires, the lift-killing spoilers, and those 1,000-degree carbon composite brakes, every single element perfectly compensates for the other. They work in absolute harmony to turn massive kinetic energy into a controlled, safe stop.
It kind of completely changes how you experience a landing, doesn't it? So, I want to leave you with a thought for the next time you hear those engines roar and reverse and you feel yourself being pushed forward into your seatbelts. Knowing exactly how much intense heat, friction, and pressure those tires and brakes are handling right beneath you, does that make you feel more comfortable or maybe a little less comfortable during your next flight? Keep all that invisible engineering in mind next time you travel. Thanks so much for joining me for this explainer, and keep questioning how the world around you actually works.